This is Chapter 6, Lesson 7. In this lesson, we will talk about intermolecular forces. Now, intermolecular forces are also called van der Waals forces, after Mr. van der Waal, are the forces between molecules. So, inter actually means between, and here are two molecules. Here's one molecule, here's another. This force here is the intermolecular force. So notice it's a dotted line. Now the dotted sort of looks maybe dashed, is actually weaker than the solid line. This right here is actually a covalent bond. Remember, covalent. This is a chemical bond, whereas this bond here is not covalent, it's a physical bond. So if you think about which one is easier to break, the physical bond is actually easier to break. And anytime you boil a substance, you're breaking this physical bond. In order to break this chemical bond, you have to undergo a chemical reaction. So we are not studying these bonds here, we are studying these bonds, intermolecular forces. There are three of them. The first one is called London dispersion force, and this is the intermolecular force between nonpolar molecules. Remember, a nonpolar molecule is a molecule that's even on both sides. So a good example of this would be something like CH4. This one is even on all sides. The whole thing is even. So there isn't a negative and a positive side. And what happens is the electrons around the molecule can move around, and they can end up on one side of the molecule, creating a momentary charge, momentary negative charge, and there will be a deficiency on the other side, creating a momentary positive charge. And this momentary charge is what gives rise to these dispersion forces. The fact that the electrons are being dispersed to different parts of the molecule is what makes them be called dispersion forces. Again, the most important thing is these are present in non-polar molecules. This is the first force. The second force is called dipole-dipole forces, and these are present in polar molecules. In fact, the reason why we call them dipole is because you have two poles from polar molecules. Here is a polar molecule, so you can think of this molecule something like HBr, for example. And this negative side means that there are more electrons on this side of the molecule. Positive side, there are less electrons on this side of the molecule. And that's because this element is more electronegative, pulling the electrons closer to itself, creating essentially a polar bond, and you get polar attractions. What happens is these molecules now stack together so that the negative and the positive of different molecules line up. And this is the force that's created. This is the intermolecular force then between these two molecules. They can also stack this way. So this is stronger than the first force because this gives you a permanent positive, partial negative, whereas the previous one give you a momentary partial positive, partial negative. This brings us to our third force. The third force is called hydrogen bonding. Now this is a special type of force, and it's created when hydrogen, you have to have hydrogen here, is bonded with one of three elements, F, N, or O. Now, if you recall, these are the three most electronegative elements on the periodic table. If you take a look at the periodic table, here is F, here is O, and here's N. So anything closer to fluorine is most electronegative, and these are the three elements closest to fluorine, the most electronegative. So what happens is when hydrogen is bonded to one of these elements, say F, the fluorine, being so electronegative, pulls the electrons off of the hydrogen so much that essentially the hydrogen is left with no electrons. The reason why this happens with hydrogen is because hydrogen is the only element on the periodic table that has only one electron. Every other element has more than one electron. So hydrogen's electron is actually pulled off of him. There are no electrons left on the hydrogen, and he becomes very positive. And this very, very positive side is what creates a very strong bond with the next molecule. So you can see this happening in water. So here is a water molecule. Remember, water is H2O. So you have an H and an O. In fact, if you take a look at it, water actually looks like this if you draw its Lewis structure. So there is a bond between H and O, and this is this hydrogen bond that's created. So what happens is the hydrogen being so positive, extremely positive, because its electron has been pulled off of it, is now very attracted to the oxygen of the neighboring molecule. And the hydrogen bond is actually this right here. The hydrogen bond is not, this is not the hydrogen bond. It's not the bond between the oxygen and the hydrogen in the same molecule. It's the bond between the hydrogen and the oxygen of the neighboring molecule. This is actually very important to know. And this hydrogen bonding can be thought of as an extreme version of the dipole-dipole forces. So dipole, remember, occurs between polar molecules. So you can say hydrogen bonding molecule is very, very polar, extremely polar. So let's kind of review all three of these, and then we'll do some examples. So hydrogen bonding is the strong force in HF, HN, HO, or any molecule that contains one of these three elements bonded to hydrogen. Dipole-dipole is a medium force present in polar molecules, and London dispersion forces are weak forces, and they're present, now this is important, in all molecules. As long as you have electrons, you have London dispersion forces. So even a polar molecule like HBr or a hydrogen bonding molecule like HF has dispersion forces because you have electrons. Those electrons can be dispersed. So in addition to being polar or having hydrogen bonding, it also has London dispersion forces. That's why usually an H bonding molecule has the strongest of all possible forces. Okay, let's go ahead and do a few example problems. And here we have three molecules, and we're asking, tell which intermolecular forces are present between these molecules. So the first thing to do is to draw out their Lewis structure so we can predict their geometry, so then we can predict their polarity. So if you draw this out, and I'll do this quickly, you can verify using the Lewis rules, but you got yourself this arrangement. And every fluorine should have an octet around it. So you should have a total of 32 electrons, and this is, it comes off the screen a bit. If you take a look, is this polar or non-polar? Now you should say, because it's evenly distributed, this is actually non-polar. Because it's a non-polar molecule, the only force present is London dispersion. This is the only force present in non-polar molecules. So the electrons can get dispersed to one side, but there is no permanent polarity to the molecule. Example 2 is pH3. Also, if we go ahead and draw its Lewis structure, what we'll see is pH3 will look like this, with the lone pair on phosphorus. Now, if you take a look, this will actually be a polar molecule because the shape of this is trigonal pyramidal. What will happen, remember, is based on the shape, the phosphorus will look like this along with 3 hydrogens. So on top you have a different picture than you have on the bottom. This molecule is actually polar. Now if you are polar, then you will have dipole-dipole forces. That's what polar molecules have. However, any molecule also has London dispersion forces, so we have to also put London dispersion forces in there. So this one has 2 possible forces. The last one then is going to be NH3, and if we draw this molecule, we'll see a very similar structure to pH3, except that you have nitrogen instead of phosphorus. This is also going to be polar because you have trigonal pyramidal geometry again. So here you have a polar molecule. So because it's polar, it will have dipole-dipole forces. Any polar molecule has dipole-dipole forces. Every molecule has London dispersion forces. And because you have hydrogen and nitrogen, you have the requirements for hydrogen bonding. In fact, this also has hydrogen bonding. And this really is the major feature of this molecule. So hydrogen bonding will also always be all 3. Dipole will be 2, and London dispersion will be 1. Good? So go ahead and try an example of your own. Go ahead and pause the video and try to do these 3 examples. And let's finish up with a discussion of how these forces can be seen at our level, on the macro level. So a good way to check or to study these forces is by looking at the boiling point. And what you do is, the higher the boiling point, the stronger the attraction between the molecules. Because if you have 2 molecules, and say HBr, here are 2 molecules, and if the force of attraction between them is very strong, this guy here, then it takes a lot of energy to break him, he will have a high boiling point. So if we take a look, we have three molecules here. We have FF, BRF, and HF. And you'll notice that FF has a boiling point of negative 188, BR negative 120, HF 19.5. So this one is actually a liquid because, roughly a liquid because it boils, you can say, higher than the freezing point of water. Now this one, because it's a liquid, has the strongest forces. It has the highest boiling point, strongest forces because it has hydrogen bonding. Notice this has H bonding. This one is next. It's gas, but it's not that tough to boil. And that's because it is polar. This one is actually polar, so it has slightly strong bonds. But this one, notice the small boiling point, which means it's going to be a gas. It's really easy to boil this guy. So he boils quite a bit below room temperature, freezing, water's freezing point. This is because he is non-polar. So you can see the effect of these forces on the physical property of boiling point. And incidentally, this is why water, the king of all chemicals, has such an unusually high boiling point, because it has hydrogen bonding. If you compare water to molecules that's its own shape and size, you'll see that water wins every single time in boiling point because of hydrogen bonding, a very, very important intermolecular force. So this completes for us video 7 of Unit 6.